Hey, it's Horner. We're going to look at the second part of problems for Chapter 2. You have a hummingbird hovering motionless beside a flower. The blur of its wings shows that they are rapidly beating up and down. If the air pushes upward on the bird with a force of 0.3 newtons, what is the force exerted on the air by the hummingbird? So we can just think about the hummingbird wing. So this would be the wing of the hummingbird. We know that the air pushes upward on the bird with a force of 3 newtons. So 0.3 newtons is the force of the air pushing up. Then the wing must be pushing down on the air. So this is the force of the wing. And because it is hovering motionless, we know that these two have to be equal and opposite. So the force of the wing is then 0.3 newtons, and it is in the down direction. So we always want that magnitude with a label, and then we have to have the direction. That's number 44. Next question is number 47. We have Margie, who weighs 543 newtons, standing on a bathroom scale, and the scale has a weight of 45 newtons. So there's several things they want us to do here. First and foremost, they want to know what force does the scale push up on our friend Margie here, and we know that that would be equal and opposite, so that would be 543 newtons, so it would be the same. They want to know, letter B, what is the interaction partner of that force? So the scale is pushing on Margie, so what we can do is let's go ahead, and here is the scale, and we've got Margie on the scale, so this is actually Margie. We know that there is a force pushing up on Margie. That is the force of the scale. And then she is pushing down, and that would be the force of Margie on the scale. So this is the force of Margie. And so when it says what is the interaction partner, it is the contact force of really her feet. So this is the force of Margie's feet on the scale. For letter C, it says with what force does the floor push up on the scale? So we know that we've got Margie standing on the scale. So there she is, and she's standing on the scale. We have the floor here, and so we've got two things pushing down on the floor, and then we have the floor pushing back up on those. So we need to have the weight of both, so that'd be 543 for Margie, plus 45 newtons, and that would be for the scale. So those two things added together end up being 588 newtons, and that would be the force that the floor pushes up on the scale. They want us to identify the interaction force of that. So the interaction partner of force exerted by the scale on the earth is the contact force of the earth due to the scale. So for letter D, this would just be the contact force on the earth, or on the ground, due to the scale. And I think over on this one we can go back and just say that the interaction partner of the force exerted on Margie by the scale is the contact force. So we can clean this one up a little bit. The contact force of Margie's feet. Margie's feet on the scale. And that would be the interaction partner for letter B. Number 52 says we have a hanging potted plant. It is suspended by a cord from a hook in the ceiling. They want us to draw a free body diagram for all of the things that we see here. So for letter A, we've got the system consisting of the plant, the soil, and the pot. We'll just draw a really quick diagram here. So here is our hook. It's connected to a rope which goes down to the pot that has the soil and the plant in it. And we just need to draw a free body diagram just for this part, just for the pot. We know that pointing down would be the force on the pot from the earth. And so we've typically called that the force due to gravity. Then we also have a force on the pot by the cord, and we've been calling that just the tension force. So we could just call that Ft. For letter B, it says the cord. And so if we just are looking at this part, which is the cord itself, we know that we have a force on the cord and that force on the cord comes from the hook itself. And then we also have a couple of forces pointing down. One of those is the force on the cord from the earth, so that's just really just the force due to gravity. And then we also have the force on the cord, and that is coming from the system of the plant, the pot, and the soil. And so we're actually going to put another arrow pointing down for it. For letter C, we have the hook, and so we're looking just at the hook part up here, and we know that we're going to draw that little hook there. We would have the force on the hook, and that's coming from the cord, so the cord's pulling down, kind of coming back up on that. I'm sorry, the force of the hook from the ceiling. So this would be the ceiling. And then we've got a couple of things pointing down. We've got the force on the hook from the earth, so that's just the weight of the hook itself. And then we also have the force on the hook from that cord that is underneath, so it's pulling on it. Finally, for letter D, now they want us to look at the system consisting of the plant, the soil, the pot, the cord, and the hook. And so now we have the force pointing up on that system from the ceiling, and we have pointing down the force on the whole system from the earth, which would just be the force due to gravity. So just a little bit more detail in these as to what's being pulled in by what thing. And that one is number 52. Number 59, they want us to go through and find, let's see, compare the weight of a 65 kilogram man on Earth with the same weight on Mars, Venus, and Earth's moon, which is our moon. So to do this, first thing we need to do is let's find out what is the weight of this man on Earth. So weight is basically just equal to mass times gravity. So our mass here is 65 kilograms. The value for gravity, we're going to use 10 just to make it simple, and 6510 would give us 650 newtons. Let's compare that to Mars, where gravity is a little bit different. So our mass is still the same, but gravity now is for Mars, so it's going to be different. So this is 65 times 3.7. Remember, our unit here for the acceleration due to gravity is a Newton per kilogram. This is 65 kilograms, so our kilograms cross off. That's why our answers are all left in newtons. Then this would be 240 newtons. For letter B, for Venus, this would be the weight on Venus. This was on Mars. Be the mass again, which never changes, but we do know that gravity on Venus is different. And so this would be 65 kilograms times the 8.9 newtons per kilogram, and that would be equal to 580 newtons. And then finally, letter C, the weight on the moon would be equal to mass times gravity on the moon, which is 65 times 1.6 newtons per kilogram, so it's a lot less. So that person would feel like that they weigh 100 newtons. And that is the end of number 59. Let's go ahead and take a look at the next one. Next one would be number 64. They want to know what is the magnitude of the gravitational force that the Earth exerts on the moon, and what is the magnitude of the gravitational force that the moon exerts on the Earth. You have to look on the inside, front, and back covers for necessary information. Our equation that we use for the force between any two very large objects due to gravity is equal to the universal gravitational constant, g, times the mass of one of the objects, so this is the mass of the Earth, times the mass of the other object, which would be the mass of the moon. And we're going to divide it by the distance between the centers of the two objects squared. The universal gravitational constant is about 6.67 times 10 to the negative 11th. If you look for the constant for the mass of the Earth, it would be 5.974 times 10 to the 24th kilograms. We're going to multiply that times the mass of the moon, which would be 7.35 times 10 to the 22nd kilogram. So remember, those are things that we'd have to look up. Those are in your book on the inside or the back cover. Then we've got the distance between the two, which is another number they would have to give you, 3.845 times 10 to the 8th meters, and that's the difference between the two distance-wise, and we need to square that number. If you do your math, you're going to end up with 1.98 times 10 to the 20th newtons. They want us on letter B, so that was letter A. Letter B, they want to know what's the magnitude of the gravitational force that the moon exerts on the Earth. Remember, Newton's third law says that every action has an equal and opposite reaction, so your number should be exactly the same, 1.98 times 10 to the 20th newtons. And that one is number 64. For number 69, this one's a little bit more lengthy, but pretty easy to solve as you go through. So it says you grab a book, you give it a you give it a quick push across the top of a horizontal table. After a short push, the book slides across the table, and because of friction, comes to a stop. So they want us to draw a free body diagram of the book, while here first we are pushing it. So we're going to just go ahead and put a dot. We know that we have the weight of the book, so that'd be the force due to gravity. We have the normal force, which we're going to call Fn. We have the force on the book from your hand, so we're going to call this an applied force, APP, and that is actually bigger than the force due to friction. Here we're pushing it. It says while we're pushing it, and because we're pushing it, our push is bigger than friction, and that's why it gets to move to the right. So that's number 69, letter A. 69, letter B, we're going to draw a free body diagram of the book after I've stopped pushing it, and now it is just sliding across the table. So we still have our force due to gravity. We still have an equal and opposite force called the normal force, and we no longer have a force going to the right. We still have, though, the force of the friction to the left. So after I've stopped pushing it, it is sliding across the table, but it should be slowing down because there is now a net force going to the left. For letter C, this one is after the book has stopped sliding, what is the force on it? So we have the force due to gravity, which is the weight, and then we have the normal force, which is pushing up, and because it's stopped sliding, it's not going left and right anymore, and we don't have any forces acting on it at that point in the left or right direction. For letter D, it says, in which of the preceding cases is the net force on the book not equal to 0? And that would be both in A and in B, because in A we had a net force, so here we're just going to put F net going to the right, because it was speeding up to the right, and then here we've got a net force going to the left because friction was slowing it down. So that is 69, letter D. For 69, letter E, they want us to go through, and it says if the book has a mass of 0.5 kilograms, the coefficient of friction between the book and the table is 0.4, what is the net force acting on the book in part B? So the first thing we're going to do here is we know that going back to our drawing, we've got force of gravity down, we have the normal force, which is pointing up, and those are equal and opposite from each other. And then going to the left, we have the force of friction, and those were the only forces we had acting on it. Remember, we need to first find what is the weight, and we know that the weight, or the force of gravity, is also equal to the normal force, since they're equal and opposite. Because weight is down, it's negative, and then the normal force would be positive because it's going up. So we're going to take 0.5 kilograms, which is our mass, and multiply it times 10, which is the acceleration due to gravity. And so here we're going to get a weight, a normal force of 5 newtons. So this is 5 newtons. This is important to have because we know that the force of friction for something that's sliding is equal to the coefficient of kinetic friction times the normal force. Our coefficient of friction is 0.4, so we're going to put 0.4 here. We're going to multiply that times 5 newtons, and we end up then with a force of friction of about 2 newtons. So here it says the net force is 2 newtons, and we would say in the opposite direction of motion. So that's in the opposite direction of motion itself. And then finally for letter F, it says if there were no friction between the table and the book, what would the free body diagram for part B look like? And then they want to know if it would slow down. That free body diagram would look just like it would for part C. So we'd only have the force due to gravity, and we would have the normal force pointing up, and it would not slow down. It would just continue to move towards the right. So there's no force left or right here, but it is moving. You don't have to have a force for something to move after you've pushed it, of course. So that is number 69. The last few here are pretty easy to do. This is number 72 all the way through number 75, but they all have the same thing going on. So for the very first one, we have a crate of potatoes. Mass is 18 kilograms. It's on a ramp with an angle of 30 degrees to the horizontal. So there's our ramp. We know that this is 30 degrees to the horizontal. They give us two coefficient of friction where they want us to find the normal force and the frictional force on the crate if the crate is at rest. So what we'll do here is we're going to put a dot for our crate. We would need to put all of the forces on that crate. So we have a force going in this direction, which would be the normal force. The crate is not moving anywhere. So the other force that's pointing down on this one would be the force due to gravity. And if there's a little bit of friction, we need to put that static friction here. So this would be the force of friction, and it would be static since it's not moving, it's at rest. Looking at this picture, we need to go through and we need to define our axes. So we're going to say that this is the positive x direction, this is the positive y direction. Our normal force and our force of friction are in those two, but gravity is not. So what I'm going to do is I'm going to erase just the label here. I'm going to put it on the other side. And then I'm going to draw two components. I'm going to put those in red. So one of my components points straight down. This would be equal and opposite to the force, the normal force. Our angle here is 30 degrees, just like it is here. And then we've got another force going in this direction. This force we said is mg, or the force due to gravity, times the cosine of 30 degrees. And then this one is mg times the sine of 30 degrees. So now I have those. We're going to say that the sum of the forces in the y direction. So here is one of them in the y direction. Here's the other one in the y direction. That's equal to the normal force, which is pointing up, minus mg cosine of the angle. And because it's not going up or down here, so it's not lifting off the ramp, not going down into the ramp, those forces should be equal to 0. Which means now I can solve this for the normal force. So the normal force here is now just equal to mg times the cosine of the angle. Oops. Let's get rid of this extra 0 I put in for whatever reason. And that would be equal to 18 times, we're going to call this 10, and we call this times the cosine of 30 degrees. So that'd be 180 times the cosine of 30, and that would give us approximately 150 newtons. So that would be this normal force. The other force that we have here is the force of friction. And so we're going to say the sum of the forces in the x direction. So there's our x direction. We have, that's equal to the force of friction minus, and then notice that this one's going in the opposite direction. So that'd be mg times the sine of 30 degrees. If you then say that these, because it's not moving, is equal to 0, it's not accelerating, sorry, is equal to 0, then our force of friction is equal to mg times the sine of 30 degrees. Our mass again is 18, gravity is 10. Now we're going to do the sine of 30 degrees, and you end up with approximately 88 newtons. So the force of friction here is 88 newtons. So that is when the crate is at rest. Let's go ahead and take a look at the next one, which is number 73. The crate is sliding down the ramp. So if the crate now is sliding down the ramp, we have our same picture that we had before. So there's our ramp, here's our box. We still have the normal force. So here this is Fn. We still have the force due to friction, but now this is called the kinetic force of friction, and it's called the kinetic force of friction because now it is moving, and our direction of movement here is down the hill. So our velocity is going this way, so that's why our friction is going up the ramp. We still have our good friend gravity, force due to gravity, which is pointing straight down. We can do our components again. This time, of course, we're going to do them in blue since we did them in red last time. This will be the force due to gravity times the cosine of the angle. We also can call Fg, remember, its weight, and so it's also mg. So that's what we did in the last one. We'll just change it here a little bit. So this is Fg times the sine of the angle. And remember, our angle is here, and it is 30 degrees because it's exactly the same as the angle of the ramp, which is 30 degrees. Some of the forces in the y. So some of the forces in the y, remember these are equal and opposite, just like the last problem. So we know that this one from the last problem is already 150 newtons. Let's look at the sum of the forces in the x direction. So the sum of the forces in the x direction would be equal to the force due to kinetic friction, which we said is equal to mu k times n, and so that's equal to mu k times mg cosine of the angle. Our kinetic friction here is 0.4, so we're going to take 0.4 times 18 times 10 times the cosine of 30 degrees. If you do that math, you should end up with something close to about 62 newtons, and that is really the force of friction, the kinetic friction, and that would be up the ramp. So we want our direction there. For the next one, which would be number 74, this one we have the crate is sliding up the ramp, and because it's sliding up the ramp, our force due to friction now is going to be in the opposite direction. So let's go ahead and draw our ramp. There is our crate. Now we know that the velocity is in the up direction. We have the normal force again, which is right here. We have the force due to gravity, which is pointing straight down. We still have a force of friction, but because the ramp, we are moving in this direction, friction always goes in the opposite direction. So this would be the force of friction, and it is kinetic because it is moving. We have our components again, so we'll draw those one more time. There's our y and our x components. We know that this angle is 30, so this angle is also 30. So this is going to be Fg times the sine of the angle. This is Fg or mg times the cosine of the angle. For number 74, again, the sum of the forces in the y are really just equal to the normal force, and the normal force, again, is just equal to 150 newtons. If we look at the sum of the forces in the x direction, that's left and right, we now have the force of kinetic friction. So that's force of kinetic friction is going to be equal to the coefficient of kinetic friction times the normal force. And so here we're going to have, this is going to be equal to mu k times mg times the cosine of the angle. And so mu k is 0.4. We have 18 times 10 times the cosine of 30 degrees. And once again, we get about 62 newtons. But this time it is down the ramp. So it's essentially the same thing that we did in number 73, except for instead of going up the ramp with friction, our friction now is going down. Very last one that you need to do for this section is number 75, and it says the crate is being carried up a ramp at a constant velocity by a conveyor belt. So here it says it's without sliding. So this one's a little bit different. Oops. It's different because now we've got our ramp. We still have our box, but on top of that ramp, we have this conveyor belt. And the conveyor belt, even though it's moving, in relation to the box, it's not. So that box is just setting still right on that. So if it's setting still, we know that we still have the normal force. We still have the force of gravity, or the weight of that box. And then because it's sitting still, normally if we just set it there and there was no friction, it would move down in this direction. But because of the situation we have here, that friction is going to be pointing up the ramp. So this would be the force of friction, but it's static this time. So even though there is a conveyor belt that's moving, if I would look at this without the table, I wouldn't see any movement between the box and the conveyor belt. So here's the box. This would be the conveyor belt itself. So there's our conveyor belt. The box is sitting on it, so there is no change in position between the two. There is, if you look at the table, so the box is moving in relation to the table, but it's still stuck to that conveyor belt. So this would be the force of static friction. Once again, the normal force is going to be equal to 150 for the same reasons that it has been for each one of these. And now we want the sum of the forces in the x direction. That would be just the force of static friction minus mg times the sine of the angle. So the force of static friction is equal to mg times the sine of the angle. So that's equal to 18 times 10 times the sine of 30 degrees. And if you do that math, if you actually put in the 180 times the sine of 30, you're going to end up with about 90 newtons of static friction. And that is the end of the solutions for this set of problems.